Hello my dear students, hope you all are doing well. Today I am going to discuss with you the different types of parasympathomimetic agents. I hope you remember previous class I have showed you the classification for these, that was direct acting, indirect acting and cholinesterase reactivators. Okay, so today first that I am going to take up with you is direct acting parasympathomimetic agents. These act directly with the receptors, that means they will go and bind with the receptor and give you the cholinergic effect or parasympathomimetic effect. Okay, so drugs that bind to nicotinic or muscarinic receptors and cause the excitation of the cholinergic system, they are called direct acting parasympathomimetic agents. These are the different drugs that has been mentioned in your syllabus. Okay, in which this carbachol you have to study the synthesis. Okay, other these you have to know the structure and the uses also. Alright, so notes will be provided to you of course for the same. Next we'll go for SAR. First we'll discuss the SAR of directly acting parasympathomimetic agents. See, this is a general structure for cholinergic agents. I hope you remember the structure of acetylcholine. Okay, so we'll go for acetylcholine SAR, direct acting sympathomimetic agents. The first point says that the quaternary ammonium group, this quaternary ammonium group is essential for the binding of the binding to the cholinergic receptors. Okay, so they help in binding, and that is why this plus charge on nitrogen, that means quaternary ammonium group, is very essential for the activity. Okay, so next what is the next point? It says that replacement of ammonium group by other onium groups, for example phosphonium, sulfonium, will be loss of activity. Okay, that means the nitrogen we are trying to replace by phosphorus P or S, in that case the activity will be lost. Alright, next point, if we are having primary, secondary or tertiary amines instead of quaternary, it will reduce the activity, because as I just mentioned earlier that quaternary ammonium compound, quaternary ammonium group is essential for binding with the cholinergic receptors. Alright, the structure here you can see for direct acting sympathomimetic agents, it is consisting of three parts. First is quaternary ammonium group, then we have a ethylene chain here, one carbon here, one carbon here, that means two carbon, so it becomes ethylene group, and this is your acetyl group. You can call it acetyloxy or you call it acetyl group, both are fine. So acetyl group CH3COO. Alright, so it consists of three parts. So again the first point was that this plus charge quaternary ammonium group is essential for activity because it helps in binding with the receptor. Alright, then if you are replacing this nitrogen, okay, this ammonium group, NH group, with any other onium group like phosphonium or sulfonium, there will be loss of activity. If you are changing this quaternary ammonium compound or group into primary, secondary or tertiary, again there will be a loss of activity or reduction in the activity. Alright, if methyl group of the quaternary ammonium group is replaced by larger alkyl groups, then what will happen? They will have different activity. For example, dimethyl derivative of acetylcholine is more active than the parent drug. Here you can see, if it would have been CH3, that was acetylcholine, right? But if we are replacing one of the CH3 with a ethyl group, you are getting larger alkyl group. Okay, so there will be change in activity, and as we can see here it's mentioned dimethyl, that means 1 and 1 2, dimethyl ethyl derivative of acetylcholine, this is the structure of acetylcholine, right, is more active than the parent drug. Okay, next point, if we are replacing more than one methyl group in the quaternary ammonium group, it will lead to complete loss of activity. If suppose one methyl group has been replaced by ethyl group, if we try to remove this group also and replace it with ethyl or propyl, then there will be a loss of activity. That would be a complete loss of the activity. Okay, then ester group of acetylcholine will help in hydrogen bonding with the receptor. Remember ester group, RCOOR, right? So this ester group is essential for hydrogen bonding. Okay, this full. So it says that the ester group helps in hydrogen bonding with the receptor. If large aromatic group is inserted, it will produce cholinergic antagonist. If we are in this ester part, if we are adding cholinergic groups, if we are adding aromatic groups, there will be cholinergic antagonists produced. That we will see in cholinergic blockers later. Okay, next is acetate group of acetylcholine can be replaced by carbamate group. Okay, now most of you would have been thinking, what is this carbamate group? Some of you might know, some of you, those who don't know, here this is a general structure of a carbamate group. Okay, acetyl group for this part, right? CH3COO. Next is carbamate. They are saying it can be replaced. Alright, so this is a carbamate group. With this R on two sides, this nitrogen is a tertiary nitrogen. Okay, and then COOR. An ester with a nitrogen next to it makes it carbamate group. Alright, an example is carbachol. This is the structure of carbachol. Here you can see this is the quaternary ammonium that is compulsory for the activity, right? Then the ethylene chain, the 2-carbon chain, next to which this is the ester part. Alright, but the ester group or the acetate group has been converted to carbamate. So this nitrogen is here. This nitrogen, we are talking about this one. Okay, and then C double bond O. Here this is the C double bond O and O. Okay, and next to it is the remaining moiety, that means this part. So this is the structure of carbachol, in which instead of acetyl group there is acetate group or acetyl group, there is a carbamate group. Okay, and this carbachol is more stable than the parent drug. Alright, and also the activity is more in comparison to the parent drug. Now next is the ethylene chain will maintain the distance between ester group and ammonium group. Alright, if we are increasing the chain length, there will be a decrease in activity, but if we are branching them, it can lead to change in activity. Alright, again see, we are talking about this now, the ethylene group that they are saying, this ethylene part. Okay, what they are saying in there is that this ethylene groups helps to maintain the distance between the acetyl group and the quaternary ammonium group. Okay, if we are increasing this, that means from 2 carbon we are making it to 3 carbon, then the activity is reduced. If we are making it propylene group, activity will be reduced. But if we are branching it, then there is a change in activity. If we are branching it, that means we are not increasing the distance between this group and this group, right? We are branching, that maybe from here we are getting something, or from here we are attaching some other group. That is called branching, right? So they are saying if we are doing the branching, then there is change in activity. Example is methacholine, which is more potent than acetylcholine. See, this is the quaternary ammonium part, the ethylene bridge, and this is the acetate part. Okay, now they have branched in here. Here there is a CH3, right? So this is known as methacholine. They have introduced a methyl group in the ethylene bridge. This was the ethylene bridge. Here they have introduced a methyl group. So this is called branching of the chain. So they are branching the chain and it leads to change in activity. For example, methacholine, which is more potent than acetylcholine. Okay. Next, they are saying that ester group can be replaced by ether ketone. Alright, and these compounds are chemically stable and potent with cholinergic activity. Now, as you can see here, this if we are removing the double bond O, this is beta methyl choline ethyl ester. Okay, so here you can see this O is here and the double bond O that was present here is not there, right? So their ester has been replaced by ether. Ether is ROR, right? So this is ROR. Okay, so they are saying that ester group can be replaced with the ether ketone. Okay, and the compound will be chemically stable and potent. Example, beta methyl choline ethyl ester. Now we come to synthesis of carbachol. Before that, See, I just noticed here this is not ester, right? This has to be ether. That's a mistake in here, that I typing mistake. This is a ether. Okay, so this is beta methyl choline ethyl ether. Please do not make that mistake. When you will give in the notes, they will have ethyl ether only in that. Alright. Now, synthesis of carbachol. In this, you have choline chloride, okay, that will react with phosgene. Okay, phosgene is COCl2. What is going to happen? This will be a minus HCl at this point. This will be removed, and one chlorine from here will be removed. So it will become minus HCl, and this part will go and attach to this part. See, this complete is as such. This is the oxygen of the hydroxyl group, this one. Okay, and then we have OCCl. OCCl. Alright, so this got attached to it as such. In the next step, in presence of NH4OH, that is ammonium hydroxide, right? So in ammonium hydroxide presence, what is going to happen? This chlorine will be removed, okay, and this NH, and from here NH2 group will come and be attached to this. Okay, so this chloride got removed and you are getting NH2. So the resultant is NH2CO, CH2CH2, N CH3 whole thrice. This gives you carbachol. Okay, simple. Now, next is indirect acting agents or cholinesterase inhibitors. Alright, now how do they act? These are there is an enzyme that is acetylcholinesterase. Right, if you remember the previous video that I had uploaded, I had told you that acetylcholinesterase or cholinesterase is an enzyme which inhibits acetylcholine, right? It is involved in metabolism of acetylcholine. It will metabolize acetylcholine into acetyl group and choline group. So acetylcholinesterase is the enzyme which stops the action of acetylcholine, and what these drugs will do, which are called indirect acting agents, what they will do is they will inhibit acetylcholinesterase enzyme. Okay, they will inhibit acetylcholinesterase enzyme, and due to this it will lead to accumulation of acetylcholine in the cholinergic nerve terminals. Alright, see, if the acetylcholine is present in the cholinergic nerve terminals, okay, what happens is acetylcholinesterase will come and metabolize that acetylcholine. Okay, if it is metabolizing, it will be converted into acetyl and choline. So acetylcholine will not be able to give its action. What these drugs will do, they will stop acetylcholinesterase, or cholinesterase it's also known as. It will stop them. Cholinesterase inhibitors, the name itself says. Alright, so it will stop it, due to which the amount of acetylcholine will be increased in the cholinergic nerve terminals. And if the concentration of a neurotransmitter is increased, then obviously the biological response will also be increased. Okay, so these agents also produce effects similar to the cholinergic agents. That means whatever cholinergic agents produce effect, they produce a similar effect, because they are inhibiting the enzyme which is responsible for the metabolism of acetylcholine. So indirectly they are parasympathomimetic agents. Alright, again, cholinesterase inhibitors is then of two types, reversible and irreversible. Okay, for reversible, what is it? Reversible inhibitors, they will bind to the drug reversibly, right? The choline subside, the drug will go and bind to the choline subside reversibly, and it will cause acylation of hydroxyl group, which is present at the serine residue of the acetylcholinesterase. Okay, do not get confused. In simple words, what it's trying to say is the drug will go and it will bind reversibly to the choline subside. Okay, and it will cause the acylation. Remember, alkylation, we know acylation similarly. It will cause acylation. Where it will cause the acylation? At the active site of the enzyme. Which is the active site of the enzyme? In acetylcholinesterase structure, there is a serine residue. Okay, that serine residue, there is a OH group. That OH group, on that OH group, it will cause acylation. When the acylation is taking place at that OH group of acetylcholinesterase, then what will happen? The action of acetylcholinesterase will be inhibited. That means it will not be able to metabolize acetylcholine. Alright, they covalently will bind to the active site of the enzyme reversibly. Make sure. Okay, In case of irreversible inhibitors, what they do, these drugs will produce irreversible inactivation of acetylcholinesterase. They will inactivate acetylcholinesterase irreversibly. They will again bind covalently to the active site of the enzyme, and of course they are long lasting because they are irreversible, so they are long lasting. Okay, and these are reversible inhibitors. So you studied indirect acting agents, and again indirect acting agents or cholinesterase inhibitors is of two types: reversible inhibitors and irreversible inhibitors. You should know the examples along with structures. Alright. In this cholinesterase inhibitors we have neostigmine, of which synthesis we have to study. Now neostigmine is a type of reversible inhibitor. Okay, we just studied reversible and irreversible inhibitors, right? So neostigmine is a type of reversible inhibitor. Let's see the synthesis. In this you have N-dimethyl aminophenol. Okay, this is N-dimethyl aminophenol, which reacts with dimethyl carbamoyl chloride. Carbamate, you remember, I just taught you. So this is carbamoyl chloride, dimethyl carbamoyl chloride. Now these two react together. So what is happening in the first step? Again minus HCl, hydrogen chlorine. So minus HCl, and this oxygen will be attached to this moiety from this carbon. See, oxygen next to which is the carbon, then carbamyl moiety, you can say CON and CH3 whole twice. Okay, next step, in the presence of methyl bromide, what is going to happen is there will be methylation, N-methylation you can call it. Okay, but because there are two nitrogens, so which N-methylation we are talking about? We are talking about this nitrogen. So at this nitrogen another CH3 group will come, and this will become a quaternary nitrogen, and this compound is known as neostigmine. Okay, once again, N-dimethyl aminophenol, N-dimethyl aminophenol reacts with dimethyl carbamoyl chloride. Okay, so what will happen? Minus HCl, and then this part, this oxygen will be attached to the remaining part, that means to the dimethyl carbamoyl. So this is dimethyl carbamoyl part. Okay, next step will be methylation at this nitrogen with the help of methyl bromide. So this CH3 will come here, and this CH3 whole twice will become CH3 whole thrice, and a positive charge at this nitrogen. This is your neostigmine. Alright. Now the last type of parasympathomimetic drugs or agents is cholinesterase reactivators. Okay, in this what you need to know is, what are these drugs? They will reverse the inactivation of cholinesterase produced by irreversible agents. Just now I told you that there are two types of agents in that, reversible and irreversible, right? Indirect agents are reversible acting and irreversible acting. Those irreversible acting agents, right, whatever effect they produce, these drugs will reverse that inactivation. Okay, these agents will cause the activation of the enzyme cholinesterase. They are used in treatment of poisoning that is produced by organosulfate compounds or acetylcholinesterase inhibitors or sulfonates. See, obviously if the amount of acetylcholinesterase inhibitors, especially those which are irreversible, if that quantity is increased, then there will be very less amount of cholinesterase in the body. If that enzyme is very less, that will cause problem to us. Okay, so if in case there is a poisoning, okay, poisoning due to acetylcholinesterase inhibitors or sulfonates or organosulfate compounds, then cholinesterase activators are used to treat that poisoning. Okay, what they will do, they will react with the alkyl phosphorylated form of cholinesterase and free the active part of the enzyme. Okay, they will release the active part of the enzyme. Example is ralidoxime. You should know the structure and uses of this drug. Okay, so this is cholinesterase reactivators. Alright, that's all. With this we have covered parasympathomimetic agents. Okay, anything that you have not understood, please let me know. You can message me or mail me whatever problems you have. Now next video I will be discussing about parasympathomimetic drugs. Sorry, in this I have discussed about parasympathomimetic drugs, right? So next will be cholinergic blocking agents. Hope this today's video was clear to you. Okay, thank you class.